Lesson 27 demo. Today we learn how to solve problems where several variables are changing at the same time. These kinds of problems are called related rates problems. Water is flowing into a cone. Height is 16 centimeters, radius at the top is 4 centimeters, at 2 cubic centimeters per minute. How fast is the water level rising when the water is 5 centimeters deep, 10 centimeters deep, and 15 centimeters deep? Let's give this a shot. So we're going to draw our cone. And we're going to label the height is 16, so that's top to bottom. Let's actually do a different color there. Top to bottom 16. And it says the radius at the top is 4 centimeters. So from here all the way over to the end, 4 centimeters, obviously a smaller radius as we go down this cone. And we've got water pouring into this cone at 2 cubic centimeters per minute. And as water pours in, the cone starts to fill up, right? And so the question is, so it's filling at 2 cubic centimeters per minute. That's a constant rate at which the water is coming into the cone. But the question here is about how fast the water level is rising. That is to say, how fast, if you were just watching the heights of the water as the water rises, would the water be rising at a constant rate, or would the water be rising fast and then slow, or would the water be rising slow and then fast? So think about the answer to that question and come back after you've had a moment to test your intuition. Okay, so hopefully you said that it was going to fill in slowly and then quick. Hopefully you said it was going to fill in fast and then slow because there's not near as much space for that water to occupy the bottom. So the water level is going to rise very quickly in the beginning, but then as the cone opens up, it's going to rise slower and slower and slower. Okay, so let's see if we can actually do some specific calculations though. So we are interested in knowing something about how fast the water level is rising. So it sure feels like we should put the water at some arbitrary height, like a generic height, and let's call that h. So we're going to let h equal the height of the water at some generic moment in time. And feels like I probably should label the radius, right? Let's call it r for the generic radius at that one moment in time. And the question is asking us to figure out how fast the water level is rising. Well, we can symbolize that. That is a calculus quantity. How fast is a derivative question. And the water level is rising as time passes. And so this question is asking us to find the derivative of h with respect to time at a few moments in time. So when the water is 5 centimeters deep, when the height is 5 centimeters, how much is the h dt? That's one of the 3 questions that we're asked to find. And we are also given that the water is pouring in at a fixed 2 cubic centimeters per minute. And that is also something we can symbolize with calculus. Water is flowing in. That's again a derivative. So what is it that's changing as water is flowing in? What is changing at 2 cubic centimeters per minute? And what's changing is the volume of water in the cup. And so that is symbolized as dV dt. The rate at which the volume of water in the cup is changing as time passes is 2, and then I don't normally put units, but we'll put them here. 2 cubic centimeters per minute. And just while thinking about units, let's get the dH dt units up here. Remember, it's h units over t units here. So that's going to be centimeters per minute. Okay. And so it sure feels like we should have a formula for the volume of water that's in the cup at any moment in time, because we know something about the way the volume is changing. So that drives us to say, okay, let's come up with a formula for the volume of the cone of water. Not the entire cone, that's fixed, but the volume of just the cone of water. So that's just this stuff down here. Okay, so maybe you know the formula for the volume of a cone. If you don't, it's something that I would give you if I asked you this kind of a question on a test or a quiz. So the volume of a cone is 1/3 pi r squared h, where r is the radius at the top of the cone and h is the height of the cone, the entire height. Okay, so there is our relationship, and we are trying to get our hands on dH dt, and we know something about dV dt, so it sure feels like taking a derivative of both sides of this equation is a good place to go, because that will head us, that will give us something with the dH dt in it, and it will also give us something with the dB dt in it. So we're going to take a derivative of both sides, and in fact you could do that right now, and the technique is going to be implicit differentiation, because the underlying independent variable for all three of these variables, I see V, R, and H, but none of them is the independent variable. The independent variable is time. Time is passing. And as a result, the volume of the water in the cone is changing. And as a result of time passing, the radius of that volume of water is changing. And the height of this little cone of water is changing. So time is the underlying variable. It is for almost every related rates problem that we do. Okay, so we could do it at the moment, but at the moment there are two variables on the right-hand side, and sometimes that's just the way it is, and you can't get around that, but we can get around it here, and we're going to take the easy way out, and we're going to eliminate one of those variables right off the bat. Before we take a derivative, we're going to make this equation simpler. So taking a look at that cone, I'm going to do a cross-section of this cone. I'm going to slice it right through the middle of the cone, and I'm going to go up and down. So I'm going to get a triangle right there, as well as a smaller triangle where the water is. So I'm going to draw those two triangles over here. Not a cone anymore, just a two-dimensional triangle. And I'll label again. We know that 16 is this whole thing here, and then 4 is this distance, the radius at the top, and then H, and then R. And I see two triangles in this picture. There is the big triangle, the whole thing, and then there's the triangle from just the water. And those two triangles, if you remember some geometry from your high school days, those two triangles are said to be similar to each other. They're the same shape, same angles, but different sizes. And when you have two similar triangles, you get to write down proportions because the sides of the smaller triangle are all in the same ratio to the sides of the bigger triangle. And so that's what we're going to do. We're going to write down a proportion. We're going to say for the big triangle, we have a height of 16. And for the smaller triangle, the corresponding height is H. And because we put the 16 on top, we have to put the radius of the big triangle on top. That's a 4 divided by, and then the radius downstairs is an R. And I said radius of the triangle, I kind of misspoke. So really 4 over R isn't technically, I mean, it's fine, it's going to give us the right answer. But I suppose technically if we're doing sides of triangles, then the top side of the big triangle is 8, double 4. And the bottom side of the, the top side of the little triangle is 2R, right? 2 copies of that R. Which of course, if you reduce, you get 4 over R, which we had before. But I suppose technically we should only be putting sides of triangles in our similar triangles proportion. Okay, so that's looking good. That means that I can solve that equation for either R or H and then substitute into this equation. I don't know which one's easier. I'm going to go ahead and solve that equation for, oh, I know what I want to do. What I want to be able to do is use the dH dt, or find dH dt. So that means that I really like that H is in this equation, and I don't like that R is in that equation. And so what we're going to do is solve this equation for R, and then substitute whatever we get right there. So we solve this equation right here for R. So I'm going to cross multiply 32R equals 8H, and then solving for R, divide both sides by 32. And then we'll reduce, and we get H over 4. So the radius is a quarter of the height, which makes sense. If you look up here, the radius was indeed a quarter of the height. Okay, so now we get to substitute that into this equation. 1/3 pi something squared, and then H, and the something used to be R, but now it is the equivalent, H over 4. Much better. The right-hand side now has only one variable in it. Okay, let's clean this up before we do our derivatives. So 1/3 pi, let's square top and bottom of that fraction, H squared over 16 times H. And then one last simplification. So I see a pi. Upstairs, I see an H cubed. And then downstairs, I see a 3 times 16, that's 48. I'm going to write it as pi over 48 times H cubed. And now we're ready to take a derivative of both sides of that equation. So I'm going to write that equation over here, but with a little bit of space in front of both sides. And we're going to take a derivative of both sides of this equation, d over d something, d over d something. So what are we taking both sides? What are we taking the derivative with respect to? Is it h? Is it v? Is it the r that we eliminated when we substituted? It's none of the above. The independent variable is what has to go downstairs in the denominator here, and the independent variable is time. Time. Which makes an awful lot of sense, actually, if you look back at the green given. The thing that we're after is a dh dt, and the thing that we know is a dv dt, so we better start building things that have dt's in the bottom, and this is how we do it. Okay, left-hand side, dv dt, there's nothing to do with that, I'm just copying it. dv dt equals. Okay, the right-hand side, we're taking a derivative. Now, implicitly, so what's the derivative of pi over 48h cubed? So pi over 48 is a constant multiplier. I copy that. Derivative of h cubed is 3h squared, piece of cake. However, h is not the independent variable. H is not playing the role of x. H is a dependent variable. Every variable is a dependent variable here except for time. And so we are differentiating implicitly. In last class, we saw that when we took a derivative of anything involving a y in it, we would have to tack on a dy dx. That was like the derivative of the stuff from the chain rule after we did our ordinary derivative. And that's what we have to do here. We just did an ordinary derivative of h cubed. We got 3h squared. But then the chain rule says times the derivative of the stuff, derivative of h with respect to t. Okay, so let's cancel just a little bit. 3 and 48 reduce, 16 on the bottom. And now we're ready to start substituting in. So if we take a look, we are given that dv dt is 2. So let's write that in. 2 equals, I'll put it h squared over 16 times dh dt. I'm going to go ahead and solve this for dh dt because that was what we were after. That was the question mark from the very beginning. So dh dt equals, so if we multiply both sides by 16 over h squared, and we get 32 over h squared. I think that looks good. And now we're in a good position to answer all 3 of the questions asked back to back to back. It said way up here that we wanted to know what's happening when the water is 5 centimeters deep or 10 centimeters deep or 15 centimeters deep. Those are each values of h. So we're just going to plug them in one at a time and we'll get our 3 answers. I'll just make a little table here. H and dh dt. 5, 10, 15, so 32 over 5 squared, and 32 over 10 squared, and 32 over 15 squared. And we'll go ahead and get some decimals here. Okay, so we got 1.28 and then 0.142. And the middle one obviously is 0.32. Okay, and again, the units here for dh dt are h units over t units, so all of these are measured in centimeters per minute. Okay, so what does that mean? It means that at the moment, the height of the water is 5 centimeters. The water level is rising at 1.28 centimeters per minute. So if that 1.28 centimeters per minute were constant, then when this height right here is 5, you would see the water level rising at 1.28 centimeters in the first minute and another 1.28 centimeters in the next minute and another 1.28 centimeters in the minute after that. But of course, we know it isn't constant. This is just at that one moment in time when the height is 5. If the height is at 10, the water level is rising much more slowly, only 0.32 centimeters per minute. And if the water is 15 centimeters deep, then even slower still, 0.142 centimeters per minute. You can take a quick look at a Sketchpad file here. First thing we're going to do is just let this thing get filled up. And so first we're watching to see if our intuition was right. We thought that the height was going to change rapidly at first and then slower, slower, slower slowest at the top, and that's exactly what I see. Okay, so we got that, and then we are going to show dH dt. This is the curve dH dt as time passes. 0.407. Go. 407 centimeters per minute. That's not what we got, is it? We got 1.28. Let's pause and reconvene. Okay, so after much careful diagnosis, I found my error. I just dropped the pi. Here it is, this pi right here. I had my h squared over 16, but I just lost the pi. I'm sure you caught that way before I did. Kind of embarrassed how long it took me to find that. In my defense, I've been in this room for roughly 9 hours straight, minus half an hour for lunch. Okay, but no excuses. So we're going to put that pi where it belongs, which is underneath. Divide both sides by pi. So that is going to change these numbers here. So we'll try this again. So it should have been 32 over 25 pi, and 32 over 100 pi, and 32 over 225 pi. And we will get much smaller numbers, roughly a third of what they were before. So 32 divided by, parentheses are necessary here, 25 pi. Enter, so we got that one, that looks better. And then 32 divided by 100 pi. And then 32 divided by 225 pi. Okay, so we'll grab these numbers, roughly 0.407, 0.102, and 0.045. Okay, let's make sure. That looks good to me. All right, again, in centimeters per minute. None of the analysis we did before was invalid, right? We do still see the same behavior here that it fills up more rapidly in the beginning and then slower and slower and slower. And then we just take a quick look at our Sketchpad thing and we get exactly the numbers we expect. So here, when the height is 15, the height is changing at 0.045 centimeters per minute. It's growing, but not very quickly. But when the height was only 10, down here, it was changing at 0.102 centimeters per minute. When the height is 5, 0.407. If you keep making the height less and less and less, you can see that the height changes really rapidly. In theory, I guess that goes up to infinity, right? If you try plugging in a number just a hair bigger than 0 for the height, you have to divide 32 by pi times the height squared. That could get really, really big. So in theory, filling up like basically infinitely fast in the beginning and then slower, slower, slower until it's full. Phew, sorry about that mistake. I could redo this video, but I'm not redoing it. So we're moving on. Okay, so on page 3 of the packet, there are general guidelines about how to solve related rates problems. You will be able to use this reference sheet on the upcoming tests, that is test number 3 in the final exam, but make sure you look it over beforehand. We're going to briefly read through the process on pages 3 and 4 in the left-hand column. So let's take a quick look at page 3 here. Okay, so the left-hand column is the general guideline and the right-hand column is an example problem. We're actually not going to look at the example problem, but it just has to do with a ladder being pulled away from a wall. And so in plain English, step 1 is to read the problem, make sure you take your time to understand exactly what the givens are. Carefully define the variables, which means that some of the values in the problem will be changing. The one mistake that's really common for students to make is to plug in the given values of the variable too early. So for example, they wanted to know in the problem we just did with the cone, what's happening to, how is the height changing when the height is 5 centimeters deep? Well, we didn't put a 5 in the picture. We put an h in the picture. The h became 5 only at the end after we took the derivative. So be clear on which quantities can change. Those ones need to have variable names. And if there are some that are truly constant, then you can just put the constant. You don't need variables for those things. Draw a variable or general picture of the situation. Symbolize what rates are given to you. We wrote down dv dt equals 2 in that problem. Determine and symbolize what rate you are trying to find. For us, it was a dh dt equals a question mark. You want to find an equation that relates the important variables. That was the that was the volume of the cone of water equation. V equals 1/3 pi r squared h. There's one extra step that isn't written here. We weren't thrilled with the right-hand side of that equation because it had r and h, and we only cared about h. So we came up with the similar triangles proportion to substitute and eliminate the r. So the equation we had only involved v and h. You can't always do that, but in this problem we could. Then you differentiate implicitly with respect to the independent variable, which is almost always time. Don't forget every single variable after you do the normal derivative rule gets a d over dt. On the left-hand side, it was a dv dt. On the right-hand side, it was a dh dt. If there was still r in there and we had taken its derivative, we would have written dr dt at some point. I don't always do this, but sometimes it's helpful to redraw the picture this time with the specific constant values or value written in. Like you could redraw the thing where you like literally labeled the height of the cone of water as a 5, if that's helpful. Sometimes it is. And then maybe find the values of the other variables at that specific moment in time. This will have more meaning when you get practice. We didn't need to do this step in our example. Plug in the values for all the variables and the rates, and hopefully the only thing that's left in your equation is the desired rate. For us, it was a dh dt. In this case, it's a dy dt. Make sure that the answer seems reasonable to you. Like in our case, it was something falling. The height of the water was rising quickly at the bottom and then slowly at the top, and that was perfectly reasonable. Okay, the activities are actually just your homework, which is going to be from some scanned pages that follow. They're scanned from this particular calculus book, so I don't think you own that one. So you're doing these 6 particular problems from the scanned stuff on the next few pages, and then one problem from your textbook, different problem depending on whether you have the 5th or 6th edition. This assignment is not due next class. It's not going to be due until class 30. These problems take time, so take your time as you work through them. I will make a video of the activities. I will do these 6 problems here, but I won't make a video of the one problem from your actual textbook. So check that out if you get stuck on any of the activities.